Okay, yesterday I introduced you guys to Newton's laws and just the principles behind them, and there's a whole lot of words and not a whole lot of usage of this. So today we're going to review that real quick and then show you how we're going to be using these laws and introduce you to some of the forces that we use. So Newton's first law was the law of inertia. Okay, and the math behind it is that when the sum of the forces equals 0, then our acceleration is going to equal 0. The fancy definition is objects don't change their state of motion unless they're told to do so. Okay, the way I like to talk about it is objects keep on doing what they're doing unless something tells them to do otherwise. Okay, which brings us to our second law. So that's where the first law is where we come up with this idea of forces, because this is what does tell objects to do what they're supposed to do. So the second law is acceleration, and that gives us our net force equals mass times our acceleration. And the net force really winds up being the sum of all of the individual force vectors is going to equal our mass times the acceleration of that object. And we went into that one quite a bit yesterday. The third law is the law of interaction, and that is the force of the force that one object has on a second is equal to, but opposite in direction, to the force the second object has on the first. Okay. And so whenever two objects come in contact with each other, they create this force pair, this Newton's third law force pair. Any two objects that are exerting a force on each other have this pair. Okay, two gravitational objects exert this pair. You sitting on your chair exerts a Newton's third law pair. There's always a Newton's third law pair. Okay. So, what happens if a bug hits the windshield of a truck? Okay. What's the last thing that goes through a bug's mind when it hits the windshield? Well, its rear end is the last thing that goes through bugs. So. What? Okay, so when a bug hits the windshield, okay, the force that the bug exerts on the truck is equal to the force that the truck exerts on the bug. However, one of these two things is more able to withstand this force than the other one, and the other one gets utterly decimated. And if you want proof, you can look at the windshield of my car, because I drove to Selma last night. So there will be plenty of bugs. Bugs all up in my grill. Okay. So. Okay, which brings us to an interaction diagram. So imagine that we have a book on a table. We need to start describing our forces and being able to draw pictures of all of our forces. So we're going to start with a book on a table. Okay, so the purple thing is the book. It has a very thick cover, particularly compared to the thickness of the table. But suspend your disbelief for a moment and imagine that the book is actually on a sturdy enough table to support it. Okay, so that's the book. That's the table. There's the ground. So what are the forces that we have going on here? Okay. So we're going to draw vectors for all of the forces involved. All of them. All right. So we have this one. This is going to be the force of the earth on the book. Okay, so this right here, this is going to be the force of the earth on the book. Okay, then we're going to have another force pointing up, and the pointing up on the book, and that's going to be the force of the table on the book. So these are just the forces that are on the book, but we have so many more. We've got the force of the earth on the table pulling it down. We've got the force of gravity. I don't know if you guys saw it over here. It's over here on the leg. This is the force of the ground on the table. These two are a Newton's law pair. The force, I'm sorry, no they're not. No, I lied. This is the table is getting pulled down by the earth. The ground is pushing up on the table. Okay, the book is actually exerting a force on the earth. Think bug in the windshield thing. Right? The book is exerting a force on the earth. It's not a whole lot, but it's equal to the force that the earth is exerting on the book. Okay, it's a mess, and we could keep going. There's still a few more. I didn't draw them all. Okay, but we could keep going, and it's ugly. So what do we do when we're analyzing our forces? Okay, we need to isolate the object that we are talking about, and in this case, we're going to isolate the book. And to do this, we draw what are called free body diagrams. So when we draw a free body diagram, for this particular case, we look at the book only and the forces that are acting upon the book only. Now, we will be developing more complicated systems later on when we have to look at the forces on multiple objects. But to start with, we just draw the free body diagram on the book alone. And in this case, the forces on the book, we have the force of the earth on the book, and we have the force of the table on the book. There should be a vector there. Okay, so now we look at, and we know according to Newton's second law, that the net force on the book equals its mass times acceleration. However, describe the motion of the book if it's sitting on the table. Look at your physics book. What is it doing right now? Okay, it's just sitting there. Okay, is it accelerating? No, at least not on our flat Earth inertial reference frame that we're talking about. Technically, it has a little bit of centripetal acceleration because it's orbiting the Earth with the rest of us while we're standing on it, but let's not worry about that right now. Is it accelerating? No, it has no acceleration relative to the rest of us. So that means that acceleration right there, the F net equals ma, that acceleration equals 0, so the net force on the book equals 0. And that gives us that the force on the book, the force of the earth on the book, plus the force of the table on the book equals 0. The sum of our forces equals 0. Now, one of them is in the positive direction, one is in the negative direction. Okay, and that's where we start getting some equal and opposite forces going on. Because if the force of the earth on the book would be down, and that would be equal to the negative force of the table on the book, which would be going up, which means they're in opposite directions, but they're equal to each other. Okay, now, this is a very simplistic example, of course. Okay, things get much more complicated. So, we have the procedure. And you are going to title this, The Procedure. And guess what you're going to use to solve all of our Newton's law problems? The procedure. So, okay, step one of the procedure. cut a hole in a box. No. Step 1 of the procedure is given, find, solve with a picture. You lazy bums that don't like to draw pictures, that don't like to follow procedures, follow this procedure. Draw a picture. It is absolutely essential that you draw a picture representing what is happening. Number 2, draw an FBD. Heretofore in this class referred to as an FBD, the free body diagram. You will not see me actually write out free body diagram ever again. Number 3, make her open the box. No, 3, choose a system of axes. Okay, this is a non-trivial step. You will have rotated forces, and you'll need to choosing the axes may be important. You may want to rotate your axes based on what forces are acting upon your object. Okay, and you then express your forces with the IJK components along the axes that you choose. Number 4, we use Newton's second law for each of the 3 directions. The sum of the forces in the x equals mass times the x acceleration. Sum of the forces in the y equals the mass times the y acceleration. And the same thing for z. We don't do a whole lot of the third dimension in here. But it's there, and you could. Okay, and then 5, we solve for the unknowns. Okay, there's usually only 1. Sometimes there's 2. Okay, which brings us to the special forces. No, we are not talking about force recon or the para jumpers or green berets or seals. Yeah, I think those are the special forces. The first one is the force due to gravity, or it is W for weight. I don't like using W, I like using F sub G. Just it's more descriptive that way. However, it is the force due to gravity. The force due to gravity is close to the Earth is mg. It is the mass of your object times g, the negative 9.8 meters per second squared. That is the acceleration of gravity. Yeah, or easily approximated to 10. Okay. Then there is N, which is the normal force. I will sometimes, out of habit, draw an F perpendicular, because that is what normal means in math. Okay, it doesn't mean regular. It doesn't mean ordinary. Okay, normal is the fancy math term that means perpendicular to a surface. Okay, lines are perpendicular to each other, but a vector that is perpendicular to a plane or some surface is normal. Think of it as you can have a normal line to a curve. Well, think of it like this. A radius is always perpendicular to a tangent line, correct? On a circle? Okay. The radius would be in the normal direction for any kind of curve, for a curved surface. Okay, there is a tangent plane for a curved surface, and that tangent plane is defined by the normal vector to that surface. Does that make sense? So it is perpendicular to the plane, and there's only one normal vector that's perpendicular to a plane. And so this is what the normal force, where that normal comes from. And it arises from two objects coming in contact with each other. So whenever you have two things in contact with each other, they are exerting some minuscule amount of force with each other. So if you put your hands together, okay, your left hand is exerting a normal force on the right, and the right hand is exerting a normal force on the left. Okay, the chair is exerting a normal force on your bum. Okay, keep pointing directly up. There is a normal force on the table pushing up on your book. This is very often the Newton's third law pair to gravity. When you have something sitting on top of something else, you have the force of gravity pulling down, and then you have the object that's keeping it from accelerating to the ground pushing up on it, and that would be the normal force. You follow that? Okay. Then we have T for tension. This is the force that comes from two linked objects. That is always a pulling force. Okay? There's a common phrase in Middle America called "you can't push with a rope." Okay? You can pull with a rope, but if you push with the rope, you're not going to get much help. So the tension is the force that comes from the pull of a rope. Okay, or a chain, or a cord, or some sort of linking contraption. Okay, and then we have applied force. F sub A is an applied force. And this pretty much constitutes everything else. Now, I've left out an important one. We're going to cover it more tomorrow or the beginning of next week. Okay, we've left out friction. Friction is a force. We get deep into friction. Okay, so applied force applies to just about anything else. Okay, so here's our example of how to use the procedure. Given that we have a crate, because physicists love crates. This is what? There's a crate on a floor. Okay, we have a crate on the floor, and it has a mass of 50 kilograms. Okay, this is also in Mr. Allen's perfect world, so there is no friction on the floor. A world with no friction would be very, very interesting. Nice one, Nick. It would be pretty slick. All right. So this is Mr. Allen's perfect world. All right. The crate experiences a rightward force of 70 newtons. Okay, so this is our given. What I want you to do, and its initial velocity is 0 meters per second. It's from a stop. You are to find its velocity at... Whoa, that went... Oh, go back. Okay. I forgot to put stops in there. Okay, so there it was. If you want to stop the video and pause it to make sure that you to get ahead of the lecture, you can. Find the velocity at t equals 3 seconds. So that wasn't what I wanted either. It's another sneak preview. So we solve. The first thing we do is draw a picture. So there's a crate. And then we start labeling our forces. We're drawing the free body diagram. So we have a force upward. This force upward would be which one? It would be the normal force. We have force up, we have force down, and we have a force pushing it to the right. Now, in the future, we're actually going to have this guy. We'll see him winding up like this when we start doing our free body diagrams. He'll wind up over here, and where the center of your forces is the object, and all the other forces pushing it or pulling it are going out from the center. But for right now, just to illustrate this, we put it over here just to show that it is it's pushing on the crate. Okay, so that is our third force. Okay, so that's our normal pushing up. Okay, this is our applied force. And then down we have our force of gravity. Now the force of gravity is going to equal mg. Okay, we're going to choose our axes. Our axes are going to be positive y is up. And so we're choosing our y-axis. Up is our positive y-axis, and to the right is our positive x-axis. And the sum of our forces. Now, hopefully we can see, will the object accelerate? Yes, it will accelerate. We have an unbalanced force acting to the right. Will it accelerate in the y direction? No. Therefore, our normal force is equal to our force of gravity, and it is all that equals 0, and we're not worried about acceleration in that direction. We're only worried about acceleration in the x direction. So the sum of the force in the x direction equals our mass times acceleration in the x direction. And the sum of the forces in our y direction equals normal plus mg, which equals 0. Wrong button again. Okay, so our force times our accelerating force equals, or applied force equals our mass times acceleration in the x direction. And acceleration is then going to equal our applied force divided by mass, and we get 70 over 50, and I'm running out of space, so I didn't include units. But that would be 70 newtons over 50 kilograms, which gives us 1.4 meters per second squared. I didn't want to start a new screen. So if we have our acceleration, then we know that velocity equals acceleration times time. So it's going to be our 1.4 meters per second squared. There should be a squared in there. Step, step. 2. Step, step. And times 3 seconds will give us a velocity of 4.2 meters per second. And that would be our velocity at 3 seconds. And that is our example of how to go through the procedure. The problems you guys are going to do are going to be a bit more complicated, but that's part of the fun.